recording seismic waves has changed throughout time. As seismic waves arrive at a seismometer, that's what we're looking at here, they cause the pen to travel back and forth, mimicking the way the ground is moving. Okay, so as this line is moving back and forth, it's representing the way the Earth is shaking. So a seismometer detects and records the passage of seismic waves. A seismometer detects and records the passage of seismic waves. A seismogram is the graphic plot of the waves. It plots vibration versus time. The P waves always arrive first, followed by the S wave and surface waves. Seismometers are very sensitive and will often pick up background noise. So that's why the modern seismometer, shown here in the upper right-hand corner, is now embedded in the ground to help prevent picking up too much background noise. So in the modern seismometer, these are being recorded digitally, and the digital signals can be printed out. And although the P and the S waves originate and move away from the fault rupture at the same time, again, the P waves are faster, so that's recorded first by the seismometer. A basic seismometer is just a cylinder wrapped in paper, and it rotates slowly at a known rate. A pen is suspended above the paper so that it draws a continuous line as the cylinder rotates. So that's what we're looking at in the upper left-hand corner. And the device is constrained so that the pen can only move back and forth along the red arrow directions. So this is the most basic way to do it. Again, the modern seismometer is doing it all digitally. And the way that we measure these has changed throughout time. But based on the size of the waves and the distance between their arrival, we can figure out the location of the earthquake and the magnitude of it. How big was this event? Okay, so just what I was saying, by using these seismograms from various locations, we are going to try and figure out which station was located closest to the epicenter. So I'm just starting at the top of our graph here. So we can see point A is the very first readout that we get. And things seem pretty quiet until our lines start showing up, and the number they've given us is 16.5. So that's 16.5 seconds before the waves arrived. At point B, it was 18.1 seconds before the waves arrived. So we know that point B must be slightly further away than A, right? Because it took a couple seconds longer for the waves to arrive there. At point C, it took 11.3 seconds for the waves to arrive. The next one down, point D, took 15.2 seconds to arrive. Point E took 22.3 seconds to arrive. And point F took 18.3 seconds to arrive. So each of these points is representing a seismic station. So the seismometer was sitting there recording, and it took this amount of time before our waves showed up. So our question is, which seismic station was located closest to the epicenter? In other words, which one had to wait the shortest amount of time before the waves arrived? So that should be C, right, with only 11.3 seconds. And which seismic station was located farthest from the epicenter, so it took the longest to reach? That should be E, right? E waited 22.3 seconds before the wave to arrive. determining the epicenter of an earthquake. So we were just looking at arrival times to try and figure out what was generally closer to the epicenter, and now we can get a little more precise with that. So looking at this graph, you want to label the S wave and the P wave on the seismogram. So the first waves to show up, and this is right at 0 seconds along, our time is along the bottom. So at 0 seconds, we've got our P waves arriving immediately. So I would label that with a P. And then our S waves look like they arrive around 44. So you would label that with a P. I'm sorry, an S. Those are our secondary waves, so they arrive second. So the amount of time between the arrival of our primary wave and the arrival of our secondary wave is called the SP interval. Okay, so all you have to do to calculate the SP interval is take the arrival time of our S wave, which in this case is 44 seconds, and subtract the arrival time of our P waves, which is very easy. We lucked out with this example because it's right at 0. So 44 minus 0 gives us 44 seconds, and that is what our SP interval is for this graph. Okay, so it took 44 seconds before the slower secondary waves arrived at the seismic station. Now we can use that again to determine, again, we're working on figuring out the epicenter of the earthquake, right? We want to know where it occurred. So using the SP interval to calculate the distance here in kilometers, we can figure out our distance from the epicenter. So we've got time along the y-axis here, along the vertical axis. So we want to find 44 seconds. Okay, so in between 40 and 50, there's a halfway mark just below that, and tracing that down, that gets us to about 430 kilometers. Okay, so you just find 44 on the vertical axis and trace it over to the right where it hits that sloping line, and then we carry that down to distance, and that gets us about 430 kilometers. Well, what the heck does that mean? What does this number represent? We're 430 kilometers what? This is the distance from the seismometer to the epicenter of the earthquake. It does not give us a direction. It just tells us the distance from the seismometer to the epicenter of the earthquake. Okay, so I know that it's 430 kilometers from the seismometer, from wherever these waves were measured. It doesn't say if it's north, south, east, west. It just says 430 kilometers. And we got that by using our 44-second SP interval in this handy-dandy graph. Now we're going to put these together. So looking at this, we want to describe how the distance calculated from the seismogram and the SP graph is used to determine the location of the epicenter. So that's what we're going to do here. Okay, so bear with me for a minute. We're going to step through it and explain it all. So, an earthquake is detected on the network of stations. Okay, that's what all these little red triangles are here. These are all seismic stations sitting there measuring any sort of seismic waves that are passing by. So we've got 3, ISCO, DUG, and WUAZ. So if you look close enough, you can see those are labeled 3 different seismic stations within this seismic network. So these 3 stations are selected. The time between the S and the P wave arrivals are measured and converted to distances. So first we measure them. We've got WUAZ with a 73-second SP interval, right? They tell us took 73 seconds before the secondary waves arrived. At DUG, we've got 57 seconds before the secondary waves arrived. And at ISCO, we've got 14 seconds. So using those, we can estimate a distance. So again, on the bottom, we've got the interval time in seconds. And the distances for each station are used to draw the potential location of the earthquake in any direction by making a circle. Okay, so if we start out with the first estimated distance, that is 14. Okay, so we're looking at the ISCO one that's closest to 0. So if we look over, we get 14 seconds, and we carry that over to the left to our distance in kilometers. That gives us roughly 100 kilometers. So we find ISCO on our map, and we've got a 100 kilometer distance drawn as a circle in every direction. Okay, so from ISCO, it could have been 100 kilometers north, south, east, west, we don't know, so we just draw a circle. Okay, and we do the same thing for the others. The next one is DUG. It's 57 seconds, so we carry that over, and it's roughly 550 kilometers. So around DUG, we've got a larger perimeter. It could have happened anywhere in this green circle here, anywhere within roughly 550 kilometers. Then the same thing for WUAZ. It was 73 seconds, so we find 73 seconds on our chart and carry that up and over to the left, and that's roughly around 700 kilometers. So we have this even larger red circle around WUAZ because it could have happened anywhere within that red circle. So now the location of the earthquake is where all three circles intersect. So there's this small area where all three overlap. We have now triangulated the epicenter. We have used 3 points to figure out the precise location of where the epicenter is. This is called triangulation. Okay, so back to your notes. We triangulate the location by having 3 or more seismic stations located in different regions. We triangulate the location by having 3 or more seismic stations located in different regions. Each station calculates their distance to the epicenter, and a circle is drawn out around the station. Where all 3 circles intersect is the epicenter. Okay, how many seismic stations are needed to triangulate the epicenter? At least 3. Okay, you can use more than that, but you need at least 3. So now we've talked about triangulating, figuring out the location and the distance from the earthquake. Now, equally important is the magnitude or the strength of the earthquake. So our first question in our notes is to define magnitude. Magnitude is a measure of the amount of energy released during an earthquake. Magnitude is a measure of the amount of energy released during an earthquake. Amplitude is a maximum wave height, usually measured in millimeters. Amplitude is the maximum wave height, usually measured in millimeters. So looking at this seismogram here on the left, what is the maximum amplitude? Okay, it looks like it reaches up to just below 40. And what you have to do is check both above and below the 0 line. right? Because above or below 0, we don't have negative numbers here when we're talking about movement in an earthquake, right? If it's moving either direction, the Earth is still moving, so we're still recording the strength of the earthquake here. So we can check below the 0 line as well and see, okay, it reached just about 40 there as well. So 37 millimeters is the maximum amplitude here. That is the furthest from 0 our line gets on this graph. All right, so this is one way to measure the size of an earthquake, and it's called the Richter scale. R-I-C-H-T-E-R, the Richter scale. So when you hear about magnitude of an earthquake, oh, that was an 8.5, that was a 6.0. Those are magnitudes on the Richter scale. In the Richter or local magnitude earthquake scale, there's a relationship between the distance from the station and the maximum amplitude of the S wave and the magnitude of the earthquake. So plotting several stations that record the earthquake confirms the Richter magnitude. Okay, so you can look on the image on the right, this plot on the right, we're connecting amplitude and distance for the 3 stations we were just looking at in our previous example. We've got WUAZ connecting the amplitude and the distance, ISCO connecting the amplitude and the distance, and DUG connecting the amplitude and the distance. So where those all converge, where they overlap in the center, shows us what the magnitude was. So the magnitude of this earthquake that from this example is right around 4.0. What is the maximum amplitude in this seismogram? So what you want to look for this, I put a red line in. You're looking for the furthest distance from that 0 line. So if we just look for height above the 0 line, that furthest point is in between 150 and 200. Okay, but you always want to check below, and so we can see it's where that red line is. It's just past 200. So the maximum amplitude in this seismogram is 210 millimeters. The example in this graph, in the black that you have on your notes, is showing us an amplitude of 23 millimeters. You can see that on the right. And a distance of 210 kilometers. You can see that on the left. That 210 kilometers is based on an SP interval of 24 seconds. So if you look at 210 kilometers on the distance line on the left, on the right side of that line, it's showing you the SP times in seconds. So 210 kilometers is the same as 24 seconds. Okay, when we connect those two dots, when we connect our distance and our amplitude, that overlaps right at the 5. So we know on the Richter scale, this earthquake was a magnitude 5. Okay, so doing that yourself, what is the magnitude of an earthquake if the amplitude is 2 millimeters and the distance is 300 kilometers? So I went ahead and put a blue dot at 2 on the amplitude, which is the line on the right. I put a blue dot on the 300 on the left, which is the distance, and then where they overlap, that gives us our magnitude. So our magnitude is right around 4. We had a magnitude 4 earthquake if our amplitude is 2 millimeters and the distance is 300 kilometers. So you should be able to do this type of problem to figure out the magnitude and the previous one to figure out what the maximum amplitude is. And if you're having trouble seeing the images on the quizzes, what you can do is hold down the control button and hit the plus sign. That will zoom in on your browser, and then if you want to zoom back out, you hold down the control button and hit the minus sign. And that can make it much easier, especially for some of these graphs where you really need to be able to see what numbers you're looking at.